Okay, I'm going to be talking about stirring by microswimmers and how they interact with boundaries. It's going to be about how to model phenomena. So one example of looking at how marine organisms or swimmers stir their environment goes back to the experiments of Katia and Dabiri in 2009, and they looked at transport by jellyfish. So they actually went to Papua New Guinea in this lake that's full of jellyfish, and they looked at how individual jellyfish drag dye around as they swam. And you can see the dye gets trapped quite a long time behind the jellyfish. In fact, this was about the time where there was quite a lot of interest in looking at biomixing, which is the idea that marine organisms might have a role in mixing the ocean. The idea goes back to Walter Munk in the 1960s, but he dismissed it after doing a kind of back-of-the-envelope calculation, and it was revived in the 2000s by Bill Dewar and many others who kind of said that the estimate turbulent dissipation was kind of much higher than people would have thought before. Since then, I think the consensus is that the effect is probably negligible. In large part, this is due to stratification in the ocean. So it's quite difficult to do significant overturning of the ocean with such small-scale effects. But my focus today will be more on the fact that this could have a local impact. So it's not completely, it's still not thought to be completely relevant. It's just that people think that it's probably more relevant to things like school of fish or colonies of copepods or things like that. But in particular for microorganisms, it's still quite relevant. And in particular, it's relevant because there's some nice experiments. This is, and I mean experiments where you can actually measure the displacements of small spheres. So this is an experiment by Jerry Golov's group, and there are similar experiments also in Ray Goldstein's group. Starts around 2009. This is experiments on Chlamydomonas renarti, which is a swimming algae with two flagella in the front. And what they did is they put some little beads in a fluid, and then they saw how those little beads moved as microswimmers swam past them. The nice thing is you can track the motion of all these beads, so you can kind of compute the displacement of all these beads as a function of time and then make a histogram how they're displaced. So we'd like to reproduce the data for this experiment, and I'll show you the data later, but let me tell you a little bit about modeling. So the idea of looking at the drift due to a swimming body or a moving body goes back to Maxwell in 1869, who has these beautiful drawings and these beautiful calculations predicting the shape of a trajectory due to a moving cylinder in an inviscid flow. So this is in 1869. This is actually often called Darwinian Drift due to a paper by Charles G. Darwin, the grandson of Charles Darwin, Evolution Darwin, who wrote in 1953 about this kind of drift. But really, it should probably be called Maxwellian drift. But in any case, everything is called after Maxwell. But I suppose there's a lot of things called after Darwin as well. It's just a different Darwin, so maybe he deserves his time in the sun. So these little trajectories are called elasticas in the paper. So the way we use this in modeling, you'll see in a second. So I'm going to show you a movie now of a collection of microswimmers that are just modeled as just cylinders in the flow. This is a two-dimensional flow, and the little line here shows in which direction they're swimming. All these swimmers are actually going to be swimming in a straight line with periodic boundary conditions, but at the origin here is a reference particle, and we're going to be looking at the drift exerted on this particle by all of these moving particles. And so the microswimmers, again, are just moving in a straight line, but as they move, they come near the particle, and they sometimes kick it. And then it undergoes one of these elastica trajectories that we saw in Maxwell's experiment, or Maxwell's calculation. So it's a sequence of these elastica trajectories, except they're randomly oriented and randomly, the amplitude is random. It has to do with the frequency of near encounters of the microswimmers with this reference particle. So you can already see some interesting questions, like if I try to compute the effective diffusivity of this process, so how does it converge to a random walk in the large scales, is the most important effect dominated by near collisions or far collisions? Because there's this competition that near collisions have a bigger effect, but they're much rarer, whereas in the far field, it's much more common to be far from a particle, but you displace the particle less. So this is from my paper with Steve Childress in 2010, and then later on there's a paper with George Lin where we included viscous effects that I'll be talking about. So here's the strategy for computing the probability density, or the PDF, of particle displacements due to a swimming organism. So first, key is to find the distribution for a single swimmer, the drift function, in other words. Then we want to sum that over many swimmers. And in probability theory, when you add variables together, that's a convolution of probability distributions. In Fourier space, convolution is very simple. So we're going to be working mostly in Fourier space, but at the end of the day, you need to take an inverse transform. And usually, this inverse transform is exactly what gives you the central limit theorem, in the sense that you want to use the saddle point method to evaluate your inverse Fourier transform, and you find that it's dominated by the quadratic part, and that's exactly what gives you the Gaussian distribution. But here, the experiments are actually take place over a much shorter time than the central limit theorem is allowed to act. And so therefore, we're going to see large deviations from a Gaussian distribution in our calculations. Care must be taken when going to the infinite volume limit to do it properly, actually. There's some convergence issues that one has to be careful about. And in the end, you have to assume some kind of hydrodynamic model for how the particles are being displaced. That's our drift function. So here's a simple calculation. And again, I'm going to leave out a lot of the details for questions of time, but capital R here is the random displacement, the distance that a particle is displaced due to encounters with n swimmers. And lambda here is the path length of swimming of these swimmers. They've moved the distance lambda in this time. So the squared displacement actually has a fairly simple expression after making a few assumptions that the expected value of the squared displacement is this integral here over capital delta, which is the drift function. So it is the distance that a particle is displaced by a swimmer swimming at distance lambda if the particle started at position eta. So eta is like the Lagrangian variable here, the label for the fluid particle. And this integral is taken over the entire volume of space. So this integral has to converge appropriately for this to make sense. Here, n is the number density of swimmers, which you can turn into a volume fraction by factoring out a factor of the volume of the swimmer. So the crucial point is that even without assuming that the swimmers ever turn, as long as there's a collection of swimmers that are randomly oriented in their swimming directions, even if they never turn, you will get a diffusive-like behavior if the integral on the right grows linearly with lambda. In that case, the motion is immediately diffusive without even allowing for the reorientation of the swimmer. But is that really what happens? And the answer is actually yes in a couple of very important cases. If your integrand is dominated by near encounters that drag a lot of fluid along with them, then the fact that you're picking up more and more fluid as the path length goes longer means that the support of this integral here is growing linearly with lambda. So that's just a schematic for the support of the integral, meaning the dominant domain of the integral, because it's a integral over z rho here. I've written to just denote the 3D integral. So that's one case in which you get a diffusion constant right out of gate without allowing for reorientation. And that's the kind of behavior you see in my paper with Steve Childress. The other case is actually more interesting, and what you see is that the drift function, if you take the case of a stressless singularity, so meaning that microswimmers can be approximated by a singularity expansion, which starts with the Stokeslet and then the stresslet and the source, point source and source dipole, etc. All of these singularities, fluid dynamics, solutions of Stokes' equation. And the far field behavior of a microswimmer is as a stresslet. And that's because the point force for a free swimmer with no external forces acting upon it, the Stokeslet term vanishes. So you can approximate the far field drift function, which I call d here, but it's not important how to get d, but it's a relatively simple expression. But again, it's in the far field approximation. But once you get your displacement function, it satisfies this very strange scaling. Strange because this is not obvious that it should scale this way at all. But this is exactly the scaling that is required to make this integral grow linearly in lambda. It is a different scaling than the one that happens here because it's a different effect. You can see here the support of the integral does not grow linearly, but the strength of the displacement also grows with distance, because when you have viscous stresses acting very far away in a viscous fluid, you keep affecting a fluid particle for a much longer time. And so this scaling magically gives us the effective diffusivity out of this. So this is discussed in Lin et al. 2011, but also Pushkin and Yeomans have a very nice calculation where they basically obtained this more analytical form and showed that at this scaling. So the squared displacement, the mean squared displacement, is just one interesting quantity that we can compute from all of this, but it isn't the only thing. You would like maybe access to the entire probability density function, and you can do this by taking this inverse Fourier transform here for the probability density p of displacements of size x with a moving distance lambda as a function of the sample variable x. And so again, e to the minus ikx is the inverse Fourier transform, and this factor here essentially amounts to a continuous convolution of your displacement function. So there's no discreteness anymore here. Little n here is the number density of swimmers. So I refer you to my paper in 2015 for details on how to get this expression. So here little n is the number density of swimmers, and capital gamma here is akin to a rate function in large deviation theory. It has a 1 minus sinc looking kernel. And the fact that you put a 1 here actually has a lot to do with what I mentioned earlier about being careful about taking the infinite volume, the thermodynamic limit for this. Because if you take the limit of the sinc by itself, you get a divergent integral, because as k goes to infinity, sinc goes to 1, and then you get a divergent integral. So you really have to add and subtract 1. That's exactly what allows you to turn this thing into an exponential. So again, I can't go into the details too much, but there's a kind of a subtlety about being able to take that limit. Now, you basically need to evaluate this inverse transform numerically. If you had a large number density, you could use a saddle point method to get to it, but you typically don't have a large number density. You're working in the dilute limit, because in any case, you've neglected interactions between swimmers. So you can do this numerically given this function, capital gamma, and just see if the model reproduces the data. And so you need for that a way of computing a drift function. And a very, very simple model is to use what's called a Squirmer model, where you assume that the swimmer is a sphere with a tangential velocity boundary condition. So it's propulsing itself by, say, a cilia at its surface and reacting by moving in the other direction. So you get a stream function, a cylindrical stream function, which has this form. It's not too important. The important thing here is that there's a term beta, which is the strength of the stresslet term in the far field. So it's the thing that dominates when you get further and further away from the swimmer. And here's a comparison to the experiments of Leptos et al., so the Golov and Goldstein experiments from the late 2000s. And so the dots, of course, are their data, and they measured the probability density of displacements at different volume fractions, which is almost the same as number density. So this is increasing volume fraction. As you see, the displacements get bigger, the distributions get wider at higher volume fractions. So this is for a stressless strength of beta equals 0.5 was fitted here to this green distribution. That is the only fitting parameter in the problem. And then once you've fitted it once, you can vary the number density or the volume fraction to look at how it looks for the other curves, and you see that it fits beautifully. In other words, fitting only the stresslet strength gives you the entire distribution, which is extremely suggestive that the dominant effect in this case actually has to do with the somewhat far away interactions of the swimmer. So because of the large distance correlation that are created by the very viscous fluid, you don't actually need to consider what happens in the near encounters with the fluid particles, which is also the reason why this Squirmer model works. But the Squirmer model, of course, doesn't look anything like Chlamydomonas near the surface. So the mere fact that this model works so well tells you that the details don't matter so much. The near field details of the microswimmer are not that important. Now, eventually, the model predicts that all of this will eventually become fully Gaussian as a function of time. And this was confirmed. This is a reference to the paper by Leptos et al. And this graph is from my 2015 paper in PRE. So 10 years later or so, the group of Ortlieb et al. Did a more detailed experiment. Basically, now that, with experiments, of course, once you know what other things to look for, you can do a different experiment. In this case, one thing they did is they ran the experiments quite a bit longer than the Leptos et al. Experiment. And they were able to confirm most of the features in this dilute theory quite accurately. In particular, the rate at which the distribution converges to a Gaussian is exactly as predicted, or is roughly as predicted by the dilute theory, and also the expression to the effective diffusivity that's given in the paper fits the data remarkably well across a different size of beads, for instance, or different speeds of swimmers. And again, this is with no adjustable parameters other than this stressless strength, which can be measured independently. And this 0.266 here is not it's just the fact that there's an integral that has to be evaluated numerically to evaluate the near field effect. But in any case, the dominant part is this second term. You can also use time-dependent swimmers. So most microswimmers have flagella or something. So this is a simple model in work with Peter Mueller, where we have a flagellum that is modeled as a point force in front of a swimmer. And you can see the drift function here now needs to be averaged over time if you're going to use it in the theory that I mentioned. The particles kind of jiggle around here. They don't actually get that far, right? They mostly go back and forth. But there's also an important observation that if you make it quite near the swimmer, you can get trapped a long time because of no-slip boundary conditions. So particles that make it near the periphery of the swimmer, the body of the no-slip body of the swimmer, can actually get dragged around for quite a long distance. So that's why the drift function, so this is a plot of the magnitude of the drift as a function of initial particle position. You can see that there's a thick yellow area here where the drift is largest. It means that particles that start initially near the body are the ones that are dragged for the longest. And these oscillations here are a kind of resonance with the period of the flagellum. So there's small variations due to the resonance. There's also a paper with Tom Morel and my colleague Saverio Spagnoli where we looked at a very simple model of a jellyfish to do simple estimates. Okay, I'm going to change topics now, and we're going to be talking about the interaction of microswimmers with boundaries. And this was inspired again by Ray Goldstein's group, sorry. Jerry Goldstein would be a nice combination of Jerry Golov and Ray Goldstein. So yeah, Ray Goldstein's group and by Kanzler. And basically they looked at the interaction of Chlamydomonas with solid boundary. And you can see that the Chlamydomonas here kind of negotiates with the wall to some degree, eventually pushes it off the wall and scatters away. So it looks a lot like a scattering event, and they did some statistics on the scattering angle, etc. So we would like here to propose a model of how to deal with these interactions with boundaries that does not involve hydrodynamic interactions. So it's very much based on the steric interaction between a swimmer and the wall. So this is a rich topic. I'm not going to be able to go over the entire literature. I want to point out the papers by Zilan and Saint-Ian, who probably is the work that's closest to what I'll be discussing here. But the point is we will focus on steric interactions, and we will basically neglect the hydrodynamics here. Of course, the hydrodynamic interactions can be put in addition, but the important novelty here is how we treat the hydrodynamic interaction, the steric interactions. So the model that we're going to use is the so-called Abp model, or active Brownian particle model, which is a very simple model. We're going to be doing it in 2 dimensions, where you have a microswimmer, and in its own frame of reference, it is moving at a constant speed u. So its increments in x are a form u dt, where capital X is the swimming direction. And the y variable and the theta variable, which is the angle of swimming, those 3 angles are driven by a Brownian motion, by a Brownian noise, dw1, dw2, dw3, with diffusivity is given as given. Of course, this is in an orientation with the swimmer, so it needs to be converted to the lab frame, and the lab frame is going to be written as little x, little y, and so you just apply a rotation to this system, and you get this somewhat complicated looking expression. But the reason why it's complicated looking to some degree is because dx is not necessarily equal to dy, so there could be different diffusivities along the different axes of swimming. And this is joint work with my student Hongfei Chen that appeared last June as a preprint, so if you're interested, it's June 2020. So immediately we start from this stochastic model and immediately find the so-called Fokker-Planck equation for the probability density of the microswimmer, and that's for a microswimmer to be at position xy with orientation theta at a time t. So this probability density evolves according to a Fokker-Planck equation, and this Fokker-Planck equation is always the form of a divergence, And there's some important things here. There's the velocity of swimming, u. So that has a u cos theta, u sine theta, which is reflecting the fact that the swimmer is trying to move forward in the direction theta. Then there's a diffusion matrix here, a diffusion tensor, which has this form. It's a symmetric matrix. If dx is equal to dy, it becomes diagonal and independent of theta. But we'll keep the dx and dy because it doesn't hurt. And then finally, there's a scalar, which is the rotational diffusion constant. So it just tells you at what rate the swimmer likes to change its direction as it goes. Note, by the way, that when I write grad here, it's merely the spatial direction. So there is no drift in the theta direction. We could put it in. That corresponds to a swimmer which has a bias and which tends to rotate at a particular direction. We just chose not to put that in, but it doesn't complicate the theory very much. Add a drift in the theta direction. So we're going to solve this PDE on domains of different shapes, but we want to figure out first what kind of boundary conditions should we be putting for these boundaries. And the way you figure this out is just by looking at conservation of probability. You say, well, the rate of change of the integral of probability is the integral of my Fourier-Planck equation, which by Gauss's theorem is the integral of the probability flux over a given surface, the bounding surface of this volume. The flux vector is just this here. So the appropriate probabilistic boundary condition, if you have a container, is to say, well, I'm going to conserve probability. In other words, microswimmers cannot leave the domain. So I'm going to locally conserve the probability flux by making its normal component with respect to the boundary vanish. That will automatically give me f dot ds is 0, and then I'll conserve probability. So this is my mixed boundary condition that I need to apply at the walls if I am to solve this PDE. Okay, but what is the boundary going to look like? Well, remember that there's three variables now, x, y, and theta. So if I give now the swimmer a particular shape, so far we've not talked at all about the shape of the swimmer. That means that if the swimmer has a certain shape, given quite arbitrarily here by a kind of teardrop shape, it means that as I change the orientation of the swimmer, I change which value of x, y are allowable. So let me show you a movie of this. So this is a movie where you force the swimmer to always be touching the wall as a function of its angle of orientation theta, and therefore that changes the minimum distance that it can be from the wall and gives you this function y star of theta that we call the wall distance function. Again, y star of theta is the minimum distance that the swimmer can be to a horizontal wall at y equals 0, given that it has swimming direction theta. So y has to be bigger than or equal to y star if there's a horizontal wall present. So here's a similar movie for what we call a needle swimmer. So that's a swimmer which is just a one-dimensional segment. And this time what we did is we moved the center at which the swimmer rotates to not be the geometric center of the needle, because the center of rotation is actually the center of hydrodynamic reaction of the swimmer. It doesn't have to be the same as the geometric center of the swimmer. So you develop this kind of asymmetry in this function y star if you move the center of rotation. So this is what this wall distance function looks like for the needle. And notice that the gray area here is where the swimmer is not allowed to go. So the swimmer has to live in the white area. We're not showing the x variable here because the x variable is essentially ignorable if the wall is along the x-axis. Here's a similar picture for an elliptical swimmer, and here's the similar movie. Again, you can get this y star of theta analytically for such simple shapes. And it's given by this function here, where this minus half a sine theta has to do with the fact that we displaced the center of swimming from the geometric center. Let me show you some simulations of a Brownian path, meaning if I start the particle and make it head towards the wall, so let me just show you the movie, it'll be clearer. So imagine that my swimmer is heading towards the wall. So in the y theta diagram, that corresponds to going down in y at fixed theta. But then eventually you meet the wall, and because of the no flux boundary condition, you're not allowed to have fluctuations that enter the wall. But yet there is still a drift being imposed here because the swimmer is trying to move at a constant velocity. So you will move down this boundary here in the y theta space until you become horizontal, which is roughly what the swimmer is doing here. And then eventually you will get lucky to get a fluctuation that makes you swim away from the wall and you'll scatter away. So notice how similar this looks to the kind of movies from the Canceller et al. Experiment. But here there's almost no physics put into this, right? In the sense that all we're saying is that the swimmer has a variable orientation, which is random, but when it comes near the wall, the fluctuations that would cause it to enter the wall due to its shape are suppressed. And therefore, it's only allowed to have fluctuations that are biased in one direction, and so therefore it orients itself away from the wall, parallel to the wall, and then away from the wall. But the fact that it orients itself parallel to the wall is exactly a function of the shape of the ellipse, the fact that this has a negative slope here. If the slope is the other way, then it will actually orient itself perpendicular to the wall. And that's what would happen, for instance, for an oblate swimmer. So now let's put our swimmer in a channel configuration. Let's give it two walls. This is actually fairly easy to do mathematically, and the important question we'll ask, for instance, is, well, there'll be two. What is the effective horizontal diffusion coefficient? So if the swimmer is now in a channel, it's allowed to move left and right in reverse direction. How do we compute the rate that it undergoes a random walk in this channel? And we can also compute the invariant density of swimmers in a channel, meaning if I wait a long time, allow the probability to settle down, where is the swimmer most likely to be? I claim that you can get all this essentially analytically using the model that I just showed you. So here's the configuration space for the channel. So this is for the needle swimmer, and one of the bottom part here is exactly our wall distance function y star that corresponds to the bottom wall. But then to get the distribution for the shape function for the top wall, you just need to kind of rotate your bottom picture. And so the swimmer is allowed to live in the white area here, and it's not allowed to enter the gray area. So again, this is called the configuration space. X, again, is completely unconstrained. And this is the case where the swimmer is just a little narrower than the channel. Therefore, it can go through these little straits here, these little holes, and that corresponds to a reversal of direction. If the swimmer goes from 0 to pi over 2 to pi, it has reverse direction in the channel. And the fact that this is a small gap means that it's quite difficult for the swimmer to reverse direction. So, in fact, of course, solving this Fokker-Planck equation is quite a challenge, but there's a nice limit. If you assume that the rotational diffusivity is small, then actually you get a beautiful reduced equation where you can write a one-dimensional PDE, a 1 plus 1 dimensional PDE, for a probability density amplitude P of theta, and the y dependence is solved for exactly. Here, I'm not going to give you the details of what all these parameters are for, but the important thing is that the shape of the swimmer and the fact that it is in a channel is entirely encoded in this function mu of theta. So the shape of the channel shows up as this one effective parameter, which contains everything you would want to know about the configuration of the swimmer and what happens when it goes in the channel, at least in this reduced model. And then you can ask nice questions like, what is the invariant density for the swimmer? Meaning, what is the steady solution to this reduced Fokker-Planck equation? And you can solve this semi-analytically. What I mean by that is in terms of integrals, which you may or may not be able to do. And you get some interesting effects, like for the fact that for an asymmetric swimmer, so if a swimmer does not have an axis of symmetry along its swimming direction, then it can have a net rotation over time, even in equilibrium distribution, meaning it will tend to hit the bottom wall in a different way that it hits the top wall, in a way that its orientation can precess over time. And so this is all predicted by the model and can be computed analytically. Basically, the average of mu gives you this rotation rate. So if mu averages to 0, then you get no rotation, and if mu is non-zero, then you get a net rotation of the swimmer. Let me show you some movies now of the invariant density that I mentioned, the invariant distribution and invariant density of the swimmer. So the swimmer tends to collect very often near theta equals 0 and pi, which corresponds to aligning with the wall. And this is the marginal distribution, the marginal density as a function of y. So you can see here the bulk of the swimmers is roughly at this distance, 0.5 and minus 0.5 away from the center line. But you can make a movie just to show what happens depending on the shape of the swimmer and depending on the center of rotation of the swimmer. So this is a movie as a function of the different shapes. Let's see, what are some interesting ones? You can see that this is roughly almost circular swimmer, in which case the walls themselves would look straight. And then the swimmer goes through various different shapes. Here's the ellipse. Still collects near the bottom, but not quite at 0, right? Not quite at 0, because the equilibrium actually involves ellipses that are slightly pointed towards the wall. And then, finally, to compute the effective diffusivity, I would like to understand how often a typical swimmer manages to go from 0 to pi, which is called a reversal, because a reversal, if you imagine what the swimmer is doing, it is hitting the bottom wall and the top wall, and once in a while it gets very lucky and manages to reverse direction. So over the large scales, if you wait a long time, it will be traveling at a constant velocity down the channel, except once in a while where it has a fluctuation that allows it to reverse direction. And so then over very long times, it'll be obeying a random walk, and you can compute the effective diffusivity of this random walk. So this reversal time, which is how long you have to wait between reversals of the swimmer on average, can actually be computed analytically quite nicely in terms of this equilibrium density that I mentioned earlier. This actually is only if the swimmer is symmetric. This expression is only valid if the swimmer is symmetric. So when the probability is small, this corresponds to a very small bottleneck that dominates the reversal time. And so from this, you can get a value for the reversal time, for instance, for the needle swimmer, and where this Peckley number is a little bit large, moderately large, and you can get an effective diffusivity out of this. So in the paper, we actually use homogenization theory to get this more accurately, but this reversal model is actually pretty simple and gives a pretty accurate answer. Okay, let me flash my conclusions quickly because I'm running out of time, but the point is that this is still a very active area of study, and I apologize for not doing justice to either the stirring biomicroswimmers and the dispersal of microswimmers. This is a massive literature. Configuration space, I think, is a lovely idea to model all these things. And is a good way to model the steric interactions, but you could include hydrodynamics in addition to that. You could include also van der Waals forces and things like that. You could allow for the bodies themselves to be deformable, like a flagellum, or the body change shape, in which case that corresponds to a moving boundary problem. And finally, I didn't show you anything about 3D here. In the axisymmetric case, it's quite simple, but in general, 3D is actually quite challenging. A bunch of references. Thank you.